Okay, we're going to try this for the first time, see how this goes. We're going to be starting the heating and air conditioning class. Now, I would suggest that you print off your PowerPoint and have this available to you while you are watching this. You can follow along on your printed copy if you have that capability. That'll help you out a lot. When people mention air conditioning, what they're usually talking about is the cold air that comes out of the vents on your automobile. So it's important to understand that when we talk about air conditioning in the automotive industry, this is a means to control the temperature, humidity, and flow of the air in the passenger compartment as a whole, not just the cold air coming out of the vents on the dashboard. This is the use of a refrigerant system, which is what we're talking about there. That's the cold air, but also the heating system, which is going to include the coolant and the heat from the engine that is going to be absorbed by the coolant coming into the vehicle, and a ventilation system to provide a comfortable environment in all weather conditions. So this is a system that is used year-round, and to a lot of people, they don't think about it other than in the middle of August when it's 110 degrees and they don't have cold air coming out of their vents, and they think that is air conditioning, which in reality is the ability to control the temperature year-round, as well as the humidity and the flow of the air through the interior compartment. So we do use a refrigerant system. That's the confined gas to provide dehumidified or dried air, and that is what you're used to in what we refer to as a Freon. And we're going to get into later on the different types of the Freons that have been used over the years. And from this point on, we're probably going to refer to that as refrigerant rather than Freon. So we need to change our vernacular a little bit on that. As technicians, we refer to that as refrigerant because different chemicals can be used for that refrigerant, which gets me into on a lot of what we're going to be talking about throughout this class is chemistry. There's more chemistry involved with this than actual mechanical components, so be ready for that. Heating system uses the heat from the engine cooling system, I mentioned that before, to supply the warm air, and really that system is pretty simple, and some of you are already used to that as well from what we've done in the lab prior to this time. So we'll be talking a little bit about how to control that hot air once that coolant has come into the heater core, and that will come later on in this. And of course the ventilation system, and that has to do with how that air is distributed or moved through the interior compartment. And that can be done through doors and ducts and vents, and even to some extent some vents towards the rear of the passenger compartment that we don't think of a whole lot because that's where the air is going to be escaping or leaving the interior compartment. Again, the term air conditioning is often used to refer to the refrigerant system. We need to kind of move away from that mentality a little bit because it is more than that. The term actually refers to all these systems working together to help control the passenger compartment environment. And we're seeing much more in recent years as we get into systems that are fully automatic or very similar to what we're used to in our residential air conditioning systems, like in your house or in a place of business. We're going to spend quite a bit of time on the principles of refrigeration. It's very similar to a home refrigerator. We don't think about it too much, but we have mentioned in the past in classes before this pandemic did attack us that when we talk about something that is cold, we're actually talking about the heat being removed from it to make it cold. So this is no different than that mentality. We are going to remove the heat from the air in the room, or in this case, the interior compartment of your car. When we talk about a refrigerator, this is a smaller version of what we're going to be talking about, and that's how a refrigerator operates. It's going to remove the heat from the items that you put in it. Some of you may have noticed before, if you bring home a 12-pack of beverage and it's warm, and then you put the whole 12-pack into the refrigerator, you go in and remove something from the refrigerator a few minutes later or a short time later that has been in the refrigerator the whole time, say like a gallon of milk, and the milk doesn't seem quite as cold. Well, that's because you just introduced a very large amount of heat into the refrigerator, and now the refrigerator is going to have to work harder to remove the heat from those items, and it's going to make everything else in the refrigerator slightly warmer as it's doing that. It's absorbing that heat, and the refrigerator is going to have to take all the heat away from it to make it cold. The Earth is a very good example of this. During the winter months, the Earth is farther away from the sun, which makes the climate colder. So therefore, if you remove the heat from something, it becomes colder, and that's the principle of this. And as you've gone through school, you've probably been taught before the three basic states of matter. This is pretty elementary, something that we are taught very early on in our education, and it's usually taught in the form of states of water. If you have water that is vaporizing, it is in the form of steam once it is boiling. And then, of course, you have the liquid state of water that we're used to and that we drink, and then you have the solid form of water, which is ice. The refrigerant that we use is no different. It's just that the state is controlled at a different temperature than what we are used to, and I'll get into that here in a little bit. Water can exist as a vapor, which is steam, liquid water, or a solid, which is ice. The temperature is what controls that state. Refrigerant is no different, except that the temperature that is controlling the state of our refrigerant is a much different temperature than what we are used to. As I mentioned earlier, heat is a controlling factor in that state of matter. The hotter an object, the faster the molecules move. The colder the object, the slower the molecules move. And so you put that into the example we used as water. You get steam as the hotter version of water. The molecules are moving much faster, and then the slower the molecules move, it appears to be a solid in the form of ice, if we're talking about water in this state. So let's get into how the heat can be transferred. These are all things that we are used to, but we just don't think about all that often. Conduction is heat transfer through objects that are touching each other. If I were to apply this into automotive, we think about the items that are in an engine, and since they're touching each other, heat is transferred from one part to another because they're touching each other. So an exhaust manifold is going to be hot because it is bolted to a cylinder head, and the cylinder head is right above the heat expansion when the air and fuel is exploded. So that is done through conduction. They're touching each other. Convection, heat is transferred caused by the air surrounding the objects. So even though the hood of the automobile may not be touching that engine, it is above the engine. You have air between the engine and the hood, and since there is heat underneath that hood, the air is actually what's making the hood of that automobile hot after that automobile has been run. So that hood is being heated through convection. And then you have radiation. This is something that we can apply to the automobile. All the time you're hearing of people warning that you don't put children or animals in the interior of an automobile during the summer months with all the windows up, because that is dangerous for that animal or that's dangerous for that child. And that's because of the heat radiating through the windows is going to make the interior compartment much hotter than the air outside of the automobile. And that is through radiation. It is radiating through the windows, and it's all closed up, and it's going to basically become an oven through the heat radiating through the windows. So when the sun shines through the windows of a vehicle, the interior parts can become very hot from heat radiation. This is a rule to fully understand what we're going to be talking about. Heat is always going to move from a hotter object to a colder object. So if you go and get a can of cold soda from the refrigerator and you set it on the table beside you right now, the heat from that table is going to be moving to the can of soda. So that can of soda, if left there long enough, is going to become warmer. The cold is going to be going away because the heat from the air around it and the heat from the table that it's setting on is going to move to the colder object. So this is a general rule to learn. This is just principles of science. Heat always moves from a hotter object to a colder object. Cold is actually an absence of heat. When one object is colder than the other, the colder object simply contains less heat. So to get something cold, you're going to have to remove the heat from it. And that's also another rule to learn as we go forward. To make something cold, you have to remove the heat from it. A British thermal unit. This is important to learn because anything that you talk about that is transferring of temperature, whether that be a water heater, a room heater, an air conditioning unit, it's measured in British thermal units, or BTUs. This is the unit of measurement for heat transfer from one object to another. So if we're trying to take a room and we're going to make it warmer, the difference between what the room was and what you can make it is measured in British thermal units. If you have a water heater, if we take basic tap water that's going to be coming into that water heater, the difference in temperature from what that water was when it came in to what it is after it's been heated by that water heater is measured in British thermal units. So BTU is the unit of measurement for heat transfer from one object to another. And this can be applied to removing of heat as well to make something colder. So anything that you are changing from hot to cold is also going to be measured in British thermal units. So that would be like a refrigerator or a freezer, or in this case, an air conditioning unit in an automobile. Cooling or heating potential is normally rated in BTUs, and that's what I just explained to you. So we get into vaporization and evaporation. This is going to be important to understand how this refrigerant works in the automobile, because it's going to have a vaporization stage and it's going to have an evaporation state as well. So anytime that we refer to a liquid changing into a vapor or a gaseous state, we're talking about vaporization or evaporation. Boiling water changing into the steam vapor demonstrates this vaporization. Water slowly changing to a vapor while sitting in the hot sun would be evaporation. So it'd be like a puddle sitting in your driveway or the parking lot, and as the heat is absorbed by the liquid and changes into vapor. Condensation is the opposite of vaporization, and this also occurs in an air conditioning system on an automobile. Later on, we're going to be talking about the different parts of the air conditioning system, and both of these, the evaporation and the condensation, are going to come into effect there. So this is the opposite of vaporization. This occurs when a vapor changes back into a liquid. And we're going to be doing that to the refrigeration or refrigerant a little bit later on. So water collecting on the outside of a can of pop, if you look over to the right or left of you, I'm willing to bet that some of you have a can of pop or a glass of beverage with you right now, and it probably has water collecting on the outside of that can or glass. That is an example of condensation because the moisture is condensing out of the air. The moisture that you're seeing on the side of that can or that glass is actually the moisture from the air around you collecting on that glass or that can. This is an example of heat given off when the vapor changes into a liquid. So, I want you to think about pressure for a second. Up until this point, the only thing we've really talked about pressure being exerted onto a liquid is the cooling system when we were in the engines class. When you think about it, the cooling system, normal operating temperature for an engine is somewhere around 220, 230 degrees Fahrenheit. Well, if you think about that, how is that possible when liquid boils at 212 degrees Fahrenheit? In theory, the liquid would boil out of every vehicle right after you get it to operating temperature. What keeps it from doing that? Well, every cooling system in an automobile is under pressure. You look at every radiator cap out there, and it has a pressure radiator cap. We are putting the cooling systems under pressure, for example, anywhere between 12 and 18 pounds of pressure. And we've discussed in the past, for every 1 pound of pressure that you put on that cooling system, it raises the boiling point 3 degrees for every 1 pound of pressure. So that is what's keeping it in a liquid state, is because we pressurize it. You are keeping it from vaporizing. So when pressure is placed on that substance, or compression, the temperature of the substance increases. The substance is going to give off heat. When pressure is removed from a substance, so for example, the cooling system that I just explained to you, if you were to take the cap off of that fully operated temperature engine, what's going to happen? Well, it's going to boil, and it's going to come rushing out of that radiator or bottle, whichever the case may be, at a very high rate, because as soon as you remove that cap, you drop the pressure. It went to, instead of being put under 15 or 18 pounds of pressure, it went to normal atmospheric pressure. You drop the pressure very suddenly, and it boiled immediately, or vaporized immediately. So this same principle can be applied to a refrigerant system. The only difference is we're not talking about a water-based liquid. We're talking about a refrigerant that has a much lower boiling point than what we're used to. So, and I'll get to that in a minute. I've got a chart here that I'm going to show you that shows the different boiling points for some common substances, as well as some refrigerants that we're going to be discussing, and I think it'll make a lot more sense there when you see that. But when the pressure is removed from a substance, the temperature of the substance drops. The substance absorbs heat. Pressure also affects change of state. When a liquid is placed into a closed container and pressurized, its boiling point increases. That's the example I just gave to you with the vehicle's cooling system. But let me give you another example. Think about a can of propane. Some of you, probably a lot of you, have used a barbecue grill at some point in time. Well, we use a can of propane to do that. Back in the days when we didn't have overfill protection devices on that propane valve, you would open up that valve of that propane, and what do you get out of it? Well, it's going to come out in a state of vapor. But what's inside that can? Most of us, if we've dealt with a can of propane, we can feel the propane sloshing around inside the can. We know it's a liquid form inside the can. Well, why is it a liquid form in the can and it comes out as a vapor? Well, it's under pressure. It's just like the cooling system on your automobile. If we put that liquid in that can under pressure, then it raises the boiling point and it becomes a liquid. But when you open up the valve and that liquid immediately hits atmospheric pressure, it's no longer under pressure. It reaches its boiling point immediately, and that's what you see is the vapor that's coming out. Let me pose a question to you at this time. What's happening to the valve itself as the propane is leaving the valve? What forms on the outside of that valve? Well, it's getting cold, isn't it? And the valve starts forming frost on the outside of the valve. Okay, that's a drop in pressure. Another example would be, maybe some of you have used the cans of air, the compressed air that we use to blow off the keyboards and electrical equipment. Well, when you press on the trigger, if you do it for long enough, then the can starts getting cold. And sometimes, if it's really humid, it even forms ice on the end of the straw or on the end of the valve as the air is leaving the can. That is an example of a drop in pressure. It's liquid inside the can, but as soon as it hits atmospheric pressure, it boils. And that's what you're seeing. So, what is a refrigerant? And this is important to note because there's some things out there that could be considered a refrigerant that you wouldn't think of as a refrigerant. Because by definition, a refrigerant is anything with a very low boiling point. So, some of you may have heard of R12 or refrigerant 12. This was common until approximately 1994. These have a boiling point of negative 22 degrees Fahrenheit. Vaporizes at room temperature. Okay, and that's what we're used to. We're around room temperature. Dichloromethane 2 is the chemical name for R12. But in our industry, this was found to be dangerous to the environment. They said it was creating an ozone hole, and so it was having a chemical reaction to the atmosphere. And we're going to get into that into the handling part of the refrigeration that's later on in this class. That's the book that I provided for you through the Moodle. R12 was phased out and replaced with R134A, somewhere around 1994, 1995. R134A has a very similar boiling point of negative 16 degrees Fahrenheit. And we're throwing numbers around here that we're not quite used to. I mean, the temperature never quite gets to that point unless you're up in Alaska or Canada. Sometimes you might get into some wind chills that are approaching that number, but this is something that's kind of foreign to us. Refrigerant 134A is less damaging to the ozone layer around the Earth, but they now have classified it as a greenhouse gas. They don't really know if it's really necessarily doing anything wrong to the ozone, but they have recognized it as collecting in the ozone and have labeled it as a greenhouse gas. There's more of that also in the booklet that you're going to be reading to get your refrigerant handling certification. So you might be paying attention to that later. So here's the chart that I referred to earlier. So we're used to water boiling at 212 degrees Fahrenheit. But look at the other items that I put here for you. Propane is negative 43 degrees Fahrenheit. That's something that we don't think about, but that's why we see it as a vapor all the time, is because in temperatures that we are used to as humans, the propane's already boiling. That's why we always see it as a vapor. R12, negative 22 degrees Fahrenheit. R134A is negative 16. Anhydrous ammonia, for those of you that have been in the rural setting and been around anhydrous ammonia, you see that it is also very similar to some of the refrigerants that we are using in the air conditioning system. And then a new refrigerant that we started using about 2015, we started seeing this in automobiles, is 1234YF. And it has a boiling point very similar to the old R12. And some of you are looking at this and thinking, well, then according to this, I could use propane or anhydrous ammonia in the air conditioning system. You're right, it would serve the same purpose. It would have the same drop in pressure. It would work as a refrigerant. Unfortunately, it would be very dangerous to use as a refrigerant, given that if you had a leak in the evaporator or you had a leak in the condenser, that could cause some very serious health issues if it was anhydrous ammonia, because it is oxygen depleting and a person would suffocate theoretically if you had an evaporator leak and using anhydrous ammonia, or it could be very flammable or explosive if you were using something like propane and you had an evaporator leak or a condenser leak in an engine bay. I once saw a video that was put out by General Motors, and I cannot find it at this time, or I would post it, and it was a video of a vehicle running with all the windows up and using propane as a refrigerant, and it had an evaporator leak, and they simulated a cigarette lighter being struck, and the vehicle immediately blew all the windows out of the vehicle because it had filled up the interior compartment with propane vapor, and it is flammable. So that is why we do not use that in the auto industry for a refrigerant. In theory, it would work, and I'm sure some of you are thinking at this point, well, we've used propane in our air conditioning systems in our tractor. Well, good for you, but understand that it is very dangerous to do so due to the explosive natures of that chemical being used as a refrigerant in air conditioning systems. So let's talk about the basic refrigeration cycle. This is going to be a little closer to the application that we're going to be doing on the automobile. The refrigerant cycle goes through 4 phases, and this would be in pretty much any refrigeration cycle, whether it be a house or a tractor, as I mentioned earlier, or an automobile. But we're going to apply this to an automobile, so it's pretty much all the same. You're going to go through a compression stage, and if you apply that to the automobile, well, every vehicle is going to have an air conditioning compressor. And that's what that compressor is doing. It's compressing the refrigerant. Then it's going to go through a condensation cycle, and that comes after the compressor. Well, every vehicle, and we've made mention of this before, does have an air conditioning condenser in the front of the automobile. This is usually right behind the grill. It's also right in front of the radiator. And it looks like just an additional radiator in front of the radiator, and that's the condenser. That's where this condensation cycle happens. You're going to have an expansion cycle, This is where this refrigerant is going to go through an expansion cycle, and that's the drop of pressure that we have talked about before. Well, if a drop of pressure is going to cause the refrigerant to evaporate, much like the nozzle on, or the valve on that propane bottle, then that's what's going to happen in this refrigeration cycle, because the next step is the vaporization. And that happens in the evaporator in the automobile. And this evaporator is typically, I'm not going to say all the time, but most of the time, typically going to be inside the dashboard area of the automobile. In other words, it's going to be in the interior compartment. So when the refrigerant condenses, heat transfers out of it and into the surrounding air. When the refrigerant evaporates, it absorbs heat to cool the air in the surrounding area. So if you apply that to what you know, in the condenser, heat transfers out. So we're giving off, we're displacing the heat. Some of you may be used to a window unit air conditioner. If you ever walked by an air conditioner, a window unit air conditioner on the outside of your house, and think about what is coming out of that air conditioning unit on the outside of your house. And if any of you have done this before, you realize that it's blowing off hot air. And that's because the air conditioner condenser on that window unit air conditioner is on the outside of the unit. And that's where we are giving off heat. And that's also why it's on the front of the car. We have a fan up there, and that fan, whether it be electric or whether it be belt driven, is going to be blowing air over this condenser, and it is transferring the heat to the air around it. Then you also have an evaporator. This is the part that's absorbing the heat and from the surrounding area. So on a window unit air conditioner, that's the part that's on the inside of the house. That's the part that's on the inside of that window. And that's the part that is going to be taking the warm air from the room, running it over that evaporator, and then because that evaporator is cold, it's going to put out cold air into the room. Well, where'd the heat go? Well, the heat was absorbed by the refrigerant, taken to the condenser, and then it was blown off of the condenser on the outside of the house. So that is basic refrigeration cycle. Same as on the automobile as it is on your window unit air conditioner or in your central air conditioning unit in your house. Somewhere on there is going to be a condenser coil and an evaporator coil. On your house, if you have a central air conditioning unit, the condenser is that square device that sits outside of your house with a fan in it, and that's the condenser. And the evaporator coil is probably somewhere in a small room, somewhere inside the house, and that's the evaporator coil. So it's the same, just on a bigger scale. So this is where we're going to start talking about the actual individual parts of the air conditioning system on the automobile. So we've already gotten into the refrigerant. This is the substance that carries the heat through the system to lower the air temperature. Compressor is the part that, obviously from its name implies what it does. It's going to pump and pressurize the refrigerant and as it forces it through the system. Now it is important to point out that not only are we pressurizing or compressing the refrigerant, but we're also pumping it through the system. So that's an important part to point out here. You're going to have a condenser. It causes the refrigerant to change from a gaseous state to a liquid state. This is causing it to give off its stored heat. You're going to have a flow control device. This is usually an expansion valve or a tube. But I think the important part to point out here is this is what is causing the pressure to drop. I gave the example earlier of the propane bottle. It's liquid inside the propane bottle, but as it leaves the valve at the top of the propane bottle and that propane hits atmospheric pressure, you have a sudden drop of pressure to cause it to be cold. So that is the flow control device in the automobile refrigeration system. Again, it's usually an expansion valve or a tube. Now, the expansion valve is something that is going to be adjustable. That valve can move. Think like a thermostat in a cooling system. If the system uses a tube, we refer to that as a fixed orifice tube. So this item right here, this flow control device that we're discussing right here, is the part that can be different from vehicle to vehicle. And I'm sorry, it is not, you cannot differentiate that, say, Chrysler product vehicles are going to have an expansion valve and GM vehicles, all of them are going to have a tube. It doesn't work that way. It's whatever the engineer decided that they felt best for that size of interior compartment or that size of engine or whatever. So GM does like to use orifice tubes, but there are some GM cars that have an expansion valve. Same with the Chrysler vehicles. Chrysler preferred the expansion valve, but we're now seeing some of them that have some fixed orifice tubes instead. So I'm sorry, I can't tell you that all one type of vehicle is one or the other. But I am going to give you some hints on how to identify as you open up the hood and look into the engine compartment on which type of system that you are working with. And you can be able to do that fairly easily by some tips that I'm going to give you. So this flow control device is what's causing the pressure drop. Putting the evaporator into a vacuum, which is causing the cooling of the evaporator. And the evaporator is the next part that we're going to be talking about, and that uses the cooling action of the vaporizing refrigerant. So we had that pressure drop, the refrigerant is now vaporizing, and if we control that and we have all the vaporization happen in one centralized area, then we can have an external fan blow over that and cool the air inside the vehicle. Now, there will be a receiver dryer or an accumulator. Now, depending on what type of device or pressure drop device you have, this part is going to be located in different places in the system. Now, that sounds confusing right now, but I'll point this out later. I've got some diagrams coming up that I'll point this out to you. If you have an expansion valve, you're going to have a receiver dryer. If you have a fixed orifice tube style system, you're going to have an accumulator dryer. Now, whichever one you have, this item's job is to remove moisture, and it stores extra refrigerant. So that is the job of this device, depending on which one you have. You will not have both. You will have one or the other. But you will have this device, and this device, the receiver dryer or the accumulator dryer, removes moisture and it stores refrigerant. Obviously, we're going to have a blower. This is something that every system has. You know that it's working because it's blowing air into your face from the vents in the dashboard. So this fan forces air through the evaporator and into the passenger compartment. I might add right here also that when we are talking about the heating side or the heater system, which is part of an air conditioning system, remember that the fan also is blowing air over the heater core, or that fan could be blowing air over both the evaporator and the heater core. That is the whole point of the air conditioning system. If we need to make that air, say, a little drier, we might add some air from the heater core to dry that air. There's going to be times when maybe the air coming out of that vent is too cold. Well, you can move the dial or move the slide on the dashboard, or in some late model cars, move the button that increases the temperature, and that is going to change the airflow from that blower fan, and it might be blowing over the heater core or a combination of the heater core and evaporator at the same time to blend the temperatures to get the desired air coming out of the vent that the driver wants. There's going to be a thermostatic switch. This shuts off the compressor when the evaporator temperature nears freezing. The whole idea is to keep that evaporator near a freezing point, so that'd be 32 degrees Fahrenheit. For if we were going to put a temperature on that, we want to keep that evaporator near that freezing. So here's the diagram that I was talking about. This diagram right here shows you the compressor. Find that there. That's where the number 1 is in the diagram right there. And if you notice in this diagram, you have 2 colors. You've got a red side and a blue side. Also note that the lines coming into the compressor and out of the compressor have a name. You've got a discharge line and a suction line. We also label these in our industry as a high side and a low side. The high side refers to a high pressure, and that would be the red side here, or the discharge side is your high pressure side. Everything in blue here is also referred to as the low pressure side, or suction side. If you're looking at the diagram, you could draw a line right through the compressor and right through the metering device as your dividing points of the system. So that means everything that's on red, discharge, high pressure. Everything in blue is low pressure or suction. So the compressor is sucking from the suction line. It's pumping or pressurizing everything in red. So to go to the text here, the compressor pressurizes the refrigerant, forces it, so there's the pressure part, into the condenser where it condenses into a liquid. So you can see there where the dots turn to a solid line, that is now liquid. Heat is transferred into the condenser and then into the outside air. Liquefied refrigerant, so anything solid here is liquid, then flows through a restriction. This could be in a fixed orifice tube or an expansion valve. As it passes through that restriction, the pressure suddenly drops. So this is like the valve on the top of the propane bottle. This makes the refrigerant turn into a vapor as it enters the evaporator. The refrigerant absorbs the heat from the evaporator, and the evaporator then becomes very cold. Remember, we want to try to keep that at the 32 degrees Fahrenheit or freezing. Here's another diagram, just another version of it. It's pretty much the same thing. You can see here that you have the compressor, discharge or high pressure sides in red, comes out of the compressor into the condenser, through the receiver dryer, through the expansion valve, there's your pressure drop, into the evaporator. Evaporator is going to be cold there, and then it's sucked back into the compressor. Now, these systems here show you that this is an expansion valve system. I mentioned earlier that the expansion valve systems use a receiver dryer. You can see that located here on the high side. It's important to note at this point that if you have the accumulator dryer system, now that means you have a fixed orifice tube for your pressure drop. So at this time, think about replacing the expansion valve with a fixed orifice tube. And if you have a fixed orifice tube, that dryer is located on the low side. Instead of the dryer being over there, the receiver dryer is located on the high side, just like the diagram here. But with a fixed orifice tube system, it will be an accumulator dryer on the low side. It'll be in the blue area. So keep that in mind here. So, as I said here, high side is the discharge side. Consists of the parts between the output of the compressor and the flow control restriction. Low side is the suction side. Consists of all the parts between the flow control restriction and the inlet or suction side of the compressor. AC compressor. Now, I've got a lot of diagrams for you here of different compressor types. We're not going to spend a whole lot of time on this. I would encourage you to open your book and look at some of those. Also, Google some of these, especially the scroll type compressor, some of the videos that are out there on Google are really interesting regarding the scroll compressor. So let's look at some of those. It's a refrigerant pump, pressurizes the refrigerant. It's either driven by a V-belt or a ribbed serpentine belt from the engine crankshaft pulley. Now, some of the late model vehicles, this is an exception to this rule, because there are cars now that do not have a belt. There is no drive belt, because there are some cars out there on the industry right now that don't need it. And if you think about that for a little bit, that we're talking about the hybrid and electric cars. As far as I know, every hybrid or electric car on the market right now does have air conditioning. But if you start thinking about how those vehicles operate, there's no internal combustion engine in an electric car. And the internal combustion engine on a hybrid car only runs part of the time. So that means we're going to have another means of running an air conditioner compressor in those vehicles. Those vehicles are going to have an electric air conditioner compressor. And quite often on an electric car, that is on the high voltage side. So just be aware of that. Different types of compressors produce an intake and an output movement, so the principle is all the same here. It's all to move or pump the refrigerant through the system and to compress the refrigerant. There are reed valves. These are simply a thin piece of metal that bends to open a passage and that bends to close that passage. And so these think like a check valve to produce a flow through the compressor. So as the piston in the compressor, if it's a piston style, as it is pushing out, the reed valve is going to bend open, allowing the refrigerant to come through the passageway. As the piston goes down in the compressor, it's going to pull that reed valve closed, not allowing anything to come in that valve. On the end of this compressor is a magnetic clutch. This is the part that you see either spinning or not spinning. It's also the item that you hear clicking on or off as the compressor cycles. And we'll be talking about the cycling of that here in a little bit. This clutch is an electric coil. It consists of a pulley, the coil, and a clutch plate. When the coil is engaged, in other words, when electricity is given to that coil, it is going to pull the plate up against the pulley, and it's going to start turning the internal guts, if you will, of the compressor. If we don't want the compressor to run, then we stop providing electricity to that coil. The clutch plate disengages and the pulley just sits there and spins, and it's not actually turning the insides of that compressor. And that's the verbiage that goes along with that. So when the electrical current passes through that coil, the clutch plate is pulled into the rotating pulley, turning the internal parts. When the compressor stops turning, well, we just turn off the electrical flow, and it disengages the plate. So let's talk about some compressor types. We've got an axial compressor, a crank style compressor, radial compressor, rotary vane. There's a scroll compressor that's becoming quite popular of late. And each one of these uses either pistons, cylinders, reed valves, or in the case of the scroll compressor, an actual two scrolls rotating within each other to create that pressure and to pump the refrigerant through the system. So I'm going to give you some pictures of each one of these types as we proceed here. And if you get curious about this, you can Google that on your own. I'm not really sure it's important for you to necessarily know how to take one apart or how to repair anything, mainly because if an air conditioner compressor fails, it's an R&R item. We just remove and replace the compressor. We don't bother rebuilding these. There was a time that we did that back in the 60s, 70s, and into the early 80s, but we've kind of gotten away from that. It's now a remove and replace item. So here are a crank compressor on the left. The one pictured was used for Chrysler product vehicles. Ford had a very similar one. GM even used some of those Ford compressors early on in the 1960s. These early crank style compressors, you may have seen one being used as an air compressor because it could be converted with an electric motor into an air compressor, and just add a tank and you've got an air compressor. The one on the right is an axial compressor. The pistons are going to be moving axially. It's got a swash plate inside, and it's going to be moving the pistons back and forth rather than up and down like the compressor on the left. This thing was used by General Motors starting in the early 1980s when we had to start downsizing automobiles so drastically as a result of the second oil embargo. CAFE requirements were getting tougher. One of the things that got much smaller and much lighter was the air conditioner compressor. And this compressor was designed by General Motors, and the pistons move radially. Think like an aircraft engine. And like the diagram on the right, these pistons are going to be moving from inward to outward as the center crank rotates. The problem with these compressors was there was a very fine O-ring in the front and the back of the compressor where the black ring was sealed to the inner housing, and it leaked refrigerant. These were very prone to leakage, and even though they had some problems, GM used it pretty much the whole decade of the 80s. So you will be seeing these. Rotary vane compressor. This is very much like the what's inside of your air impact guns they're using to remove and install bolts and nuts on your air impact. The inside consists of a drum with these vanes, and as that drum rotates, the vane has a spring behind it that's springing it out against the housing. So one side of this, if you're looking at the picture in front of you, these, for example, the upper area might be compression on one side or intake on one side and discharge on the other. So as that vane crosses over from the intake side to the exit side, it is taking the refrigerant in and then compressing it as it moves to the exit side on both top and bottom. Scroll compressors look pretty much the same as the vane compressors on the outside, but inside they are very different. And if you look across the bottom of this diagram, you'll see that as the refrigerant is pulled into the outside of the scroll there, the scroll is going to be rotating inside another scroll and is going to push that refrigerant towards the center. And as that refrigerant gets pushed to the center, it is compressing the refrigerant because it becomes a much smaller and smaller space as it gets towards the center of the scroll. And so this system confines the refrigerant into a much tighter spot. So in theory, it's much more efficient and it takes less energy to rotate it. But because the device that's actually compressing the refrigerant is not reciprocating and really not rotating either, the scrolls on these compressors are a high failure rate item. And when they fail, the compressor, it fails in a very large way. The scrolls break. I would encourage you to Google scroll AC compressor and Google video and watch some of the videos on this. So the crank compressor uses a crankshaft to pump pistons up and down. The axial compressor is going to pretty much do the same thing, but the piston is going to go back and forth rather than up and down. There's going to be a shaft, eccentric shaft. This is an egg-shaped component that causes piston movement in a radial compressor. And vanes pressurize refrigerant in a rotary vane compressor. The scroll compressors, as I said, it would be a good thing. Just again, you're not going to be rebuilding these air conditioner compressors, but it's good for you to understand what's happening inside these compressors. Do some Google imaging or some Google videos on these items if you are more curious about how they operate. So, lots of moving parts are going on inside these compressors. And with anything moving, we have to lubricate these moving parts or they're going to have friction and burn up bearings or galled or score walls, and it's not going to hold pressure. So we're using a high viscosity, highly refined oil. In other words, that's a very clean oil to lubricate the parts of the air conditioning system, especially the compressor. The refrigerant oil and the refrigerant need to be able to mix. That's very important here. As we saw in the chart before, we have different refrigerants that we are using in automobiles. Now, I doubt you're going to be running into very much R12 systems out there. Most of those are gone, and if you have an older vehicle, it's very likely been converted to one of the new refrigerants. But the refrigerant that you're using in the system needs to have an oil that is going to mix with that refrigerant. If you don't, then you have the opportunity to burn something up, and the first thing it's going to burn up is going to be your compressor. And if any of you have priced an air conditioning compressor, you know that these things can get very expensive. It's not unusual to see $300, $400, $500 air conditioner compressors. So using the correct oil to lubricate that $300, $400, $500 air conditioner compressor is essential. So you as a technician could very well put the wrong refrigerant oil into a system and burn up a brand new compressor. That would not be a good situation. On the engine bay should be a sticker somewhere that tells you how much refrigerant the system holds and what oil the system is using, and make sure that if you have to add oil to a system or if you have to replace a component, make sure that you are using the correct oil for that given system. A 134A system is usually going to use PAG or ester oil. Again, you don't want to mix these two, so you need to make sure you're putting in what the manufacturer recommends for that given vehicle. They do not mix well if you're mixing them. So if it requires ester oil, put ester oil in it. If it requires PAG oil, then you need to put PAG oil in it. Our 12 systems used mineral oil and mineral-based oil. So if you are converting, say if you have an old vintage car, pre-1994 vehicle of some type, and you are converting it to 134A, then you need to make sure that you're getting all of that old mineral oil out and that you are putting in either ester oil or PAG oil. On these systems, refrigerant hoses are high-pressure hoses designed to withstand the compressor pressures as high as 250 pounds per square inch. Special fittings are used on refrigerant hoses, and I might add that these special fittings are also different from one style of refrigerant to another. O-rings, seals, hose clamps, flared tube ends are used on the fittings to prevent leakage. You will very rarely see hose clamps anymore. That was something that we did use back in the 1960s, but starting in the 70s we went away from that. Pressures just really have gotten so high that hose clamps are not sufficient enough to hold the pressure in. If you are making repairs to hoses, it is not recommended to just cut one off and install it with a hose clamp. That is not a recommended practice. It's not if the system will leak, it is how much it'll leak. It will leak if you're using hose clamps on a new system. The pressures are just too high. The service ports are used on late model vehicles. They are extremely different from R12 to 134A systems. R12 systems used a service port that looked a lot like a valve stem on a tire. The ones used on R134A are much different. They look more like the ends of an air hose that we use with our air tools in the shop. 1234A service ports look very similar to R134A service ports, but they are in fact different, and this is done so that you will not intermix the different refrigerants. We'll learn more about that in the pamphlet that I uploaded for you for the refrigerant handling. Air conditioning condensers, we've already discussed this a little bit. Radiator-like device transfers heat from the refrigerant to the outside air. You can see in the picture here what looks like a radiator right there in front of you is actually the air conditioner condenser, and the fan behind it is what's going to blow air over it, dissipating the heat off of it. Simply a long metal tube. You can see it there as it winds back and forth between just hundreds of thousands of metal fins. The fins are there to increase the surface area, and we need to be careful. One of the things we look at as a technician is to see if that condenser is blocked. Does it have a bunch of bugs in it? Is it clogged with leaves or dirt or any other debris? Vehicles that are run on the highways or run at night, most of their mileage might have lots of bugs that have folded over the fins, and that is going to cause the air conditioning system to be less efficient. In other words, it's not going to cool as well. If this air is blocked over that condenser, the air conditioning system will not cool as well as it should. So later on when we talk about diagnosing these systems, that's one thing that you need to be very aware of. It's a very common problem that these condensers either get folded over, the fins get folded over from impacts, with small bugs over lots of miles, or this condenser gets blocked with something else. Maybe it's somebody that puts a piece of cardboard in front of the grill for the winter time so that their heater warms up faster, and they forget to take it out. We've seen that as a technician. So definitely something to look at in the diagnosis part if this air conditioner condenser is blocked in some way. This is a picture of the receiver dryer. So in the previous discussion, that means that whatever system that this is a picture out of, what type of pressure drop device does this have? Being that it's a receiver dryer, that means it's got an expansion valve, not an orifice tube. This is a receiver dryer. Again, removes moisture from the system. And as I mentioned earlier, this is normally located on the high side. We can identify this as the high side because the metal tubes going in and out of it are small diameter tubes. That is a sign that those are high pressure liquid lines. The low side of the system, the tubes are much larger because it's a gaseous state in most of the low side. So this is a receiver dryer. Again, this will be an expansion valve system, and you can tell that it is on the high side, making it a receiver dryer. Accumulator dryer. As mentioned earlier, this performs the same function as a receiver dryer. It stores and dries a refrigerant. However, this identifies whatever vehicle that this picture is taken from as a fixed orifice tube system, because if you look at the lines going in and out of this device, they are larger in diameter. Because it is near the evaporator, this identifies this component as being on the low side or the suction side of the system. So that identifies this item as an accumulator dryer. That also identifies as the pressure drop device used in this system as a fixed orifice tube. The accumulator dryer keeps liquid refrigerant from entering into the compressor, and the compressor can be damaged by liquid refrigerant. Liquids don't compress. We already know that from other things we've studied in the auto industry. And so this is going to prevent any liquid refrigerant from going any further and going to that compressor. Cannot compress a liquid. So here's another picture of the evaporator. This is with everything removed from it. This is the part that we don't normally see because it is underneath the dashboard, encased in some type of plastic housing. So like the condenser, it's a tube that is winding back and forth, mounted in cooling fins, usually mounted on the right side of the vehicle. Here in the United States, the driver sits on the left, so things like this installed in the vehicle are on the right side of the vehicle or on the passenger side of the vehicle. This typically fits in a blower housing, a plastic box of some type, either on the outside or inside of the bulkhead. We're seeing more and more often that this is now put on the inside, somewhere back behind the glove box in a plastic box. So there's the plastic box that I told you about there on the left. Picture on the right is a picture of the dashboard assembly removed or pulled away so that you can see where that plastic box is there. If that looks like a pain to replace, you are correct. Most heater core or evaporator core replacements require dashboard removal to get to them. This is going to be involved lots of small plastic parts and lots of screws removed. You need to make sure that you're keeping track of where all these items go as you're disassembling, because you're going to have to put it back. Also, you're dealing with lots of plastic parts that might break, so be cautious in removing this dash assembly as you are headed for the evaporator heater core box. Also inside that box is all the blend doors that direct the air over either the heater core or the air conditioner evaporator. We'll get more to that in a few slides. System controls. All AC systems use a compressor, condenser, evaporator, dryer, and or accumulator. However, many different devices are used to control this operation. We've already talked about the fixed orifice tube or the thermostatic expansion valve system. And those are the we're going to be discussing. The expansion tube system, also called a clutch cycling system, fixed orifice tube system. There's different names depending on the manufacturer you're talking about, but all essentially are fixed orifice tube systems. When you take your ASE test, they're going to refer to these systems as a fixed orifice tube system or an FOT system. Controls refrigerant flow and evaporator temperature by cycling the compressor on and off. If the orifice tube is fixed, that means the only way of controlling the rate of evaporation is to shut off the flow of refrigerant. And so that's how we do it. You're going to either turn off the compressor or turn on the compressor to make the evaporator colder or warmer. So on this fixed orifice tube system, it has a fixed opening, and it's going to meter that refrigerant flow into the evaporator. So going back to the propane bottle, either the valve is open or closed. The expansion tube is usually inserted into the refrigerant line near or inside the evaporator inlet. So that's important to know as far as location, because those fixed orifice tubes do get plugged up. When they're plugged up, that creates either a blockage or a much smaller orifice, which is going to cause some freezing. So something to be aware of. Two types of compressor cycling switches are used, either thermostatic or pressure. These are used in the expansion tube or fixed orifice tube systems. The thermostatic cycling switch turns the compressor on and off to maintain the evaporator temperature of approximately 32 degrees. Remember, we want to try to keep that evaporator as close to freezing without completely freezing up. So since the evaporator pressure determines the evaporator temperature, a pressure cycling switch can be used. So since evaporator pressure determines the evaporator temperature, a pressure cycling switch can be used in place of or in conjunction with a thermostatic switch to maintain the correct evaporator temperature. This sounds confusing, sounds very technical, but I think the important thing for you to remember at this point is that we are trying to maintain a temperature near 32 degrees Fahrenheit. And that is by means of either a thermostatic or a pressure cycling switch, or both. We can use both, and there's a lot of newer vehicles as we are trying to get more and more efficient using both of these. So the thermostatic switch is going to actually take a temperature of that evaporator and try to keep it there. The pressure cycling switch is going to do the same thing by means of what pressure is in the system on the low side. So either one or both of these switches can be used. But the end result is trying to keep that evaporator. So on the expansion valve system, I had mentioned much earlier that think a thermostat and a cooling system. Most of you have seen that thermostat comes out on a cooling system, and you know how that operates, that it can open and close. It's going to control the flow of coolant through the system, and it's closed when we start up the engine, and then as the engine warms up, it starts to open, allowing coolant to flow through the radiator. Well, this is essentially the same thing on the refrigerant side. This is a temperature sensitive valve that controls the refrigerant flow based on the evaporator temperature. Just like on the last style system, the end goal is the same. We want that evaporator to stay around 32 degrees Fahrenheit. But instead of constantly cycling the compressor on and off to keep that evaporator at that temperature, Instead, we're going to control the amount of refrigerant that is going through the pressure drop device or the orifice device. This is a much more efficient way of doing this. Yes, there's more moving parts, but we can more consistently and more accurately keep that evaporator at that 32 degrees Fahrenheit. Now, this system consists of a thermostatic bulb and a tube, a diaphragm, actuating pins, a valve and a seat, a metering device, and the spring. So all of those items, I mean, if we compare this to the other system, the other one's just a fixed tube that's much smaller. So the refrigerant's having to go through a much smaller tube, and then it goes into a larger opening, which is your pressure drop. Very simple. This is much more complex, but the trade-off is this system with the more moving parts keeps the evaporator more accurately at that 31, 32 degrees Fahrenheit temperature. So it's going to more accurately keep that evaporator at a constant temperature, where the orifice tube can't do that. So when the temperature of the evaporator in the bulb is too warm, the expansion valve on the thermostatic bulb places pressure on the diaphragm. This flexes the diaphragm, pushing the expansion valve open. More flow goes through it. In other words, more refrigerant is going into the evaporator, providing more cooling. If that evaporator is too cold, if it's getting too cold, then the spring in the expansion valve closes the metering orifice and reduces the amount of flow into the evaporator, which is going to make the evaporator start to warm up, and the air going over that into the vents is going to be warmer. So this is much more accurate. So we have some other controls here. We have an ambient temperature switch. Ambient temperature is going to be the temperature outside of the vehicle, ambient temperature. We need to know, going back to talking about BTUs, we need to know how hard this system needs to operate to get the interior down to whatever setting the driver put it at. There's a low pressure cutout switch. In other words, if the system doesn't have enough refrigerant in it, if the pressure's too low, then we need to shut off the vehicle. We're going to get into that. High pressure cutout switch, kind of the opposite. Thermal limiter or a superheat switch, pressure relief valve, and a WOT, that stands for wide open throttle switch, and we'll get more into that too. There's an AC switch. Sounds rather simple and redundant, but that is something that this system needs to have. So let's get into the ambient temperature switch. This can be used to keep the compressor from operating when the outside temperature is too cold. This helps prevent seal or gasket or reed valve damage. It's kind of pointless to have the air conditioning system operate if the temperature outside is actually colder than what you're going to get coming out of the vents having the refrigerant cycling. However, some of you have already noticed that during the winter time, the air conditioner compressor does cycle when you have your system on defrost. That does two things. It keeps the refrigerant cycling throughout the winter time so that we keep seals moist, we don't dry out seals and cause a leak. And that also helps in humidifying the air during the winter time. During the winter time, air gets very dry, you have loss of static electricity, so we're using the air conditioning system in the winter time to actually put some humidity into the air that is coming out of the vents. Low pressure cutout switch prevents compressor damage by shutting off the compressor when the system drops below a certain point. These systems do leak, and if there's not enough refrigerant in the system to actually pump through the system, then we need to shut off the compressor so we don't burn up the compressor. So low refrigerant could overheat and lock up the compressor. So that's why we have a low pressure cutout switch. We have a high pressure cutout switch, kind of for the opposite reason. If the compressor pressure is too high, again, we could burn up the compressor due to too high of pressures, too high head pressures, and therefore we want to shut off the compressor if that pressure gets too high. Another example of this is the DIYer. We can buy this refrigerant in small quantities almost anywhere these days, whether it be Walmart or Blue Stem or the parts store. This stuff is readily available for the do-it-yourselfer, the everyday person, to just buy a can and charge their own system. As technicians, we don't like that, because what happens in a lot of cases is that they have another problem that's causing it to blow hot. It's not the refrigerant system. And so they keep putting refrigerant into the system, expecting it to get colder, and it doesn't do so. Before you know it, you have a system that has two problems. It's got the original problem that, I don't know, might be a blend door in the dashboard or something that's not directing the air over the evaporator. Instead, it's directing over the heater core. Well, that's going to create hot air. There's no refrigerant problem at all, but because it seems that way to the uneducated, they just keep feeding refrigerant to the system, hoping to get it to start blowing cold. When in reality, what they're doing is they're overcharging the system, which is going to create high pressure, and even though the compressor wasn't the original problem, it could become an additional problem. And now the driver has two problems, and they don't even know it. So this is a very common issue, and this is why technicians really don't like that refrigerant is available to the uneducated person, because they actually do more damage than repair. Thermal limiter switch, or a superheat switch, they actually do call it that, can be used to prevent compressor damage when the refrigerant level or the oil level is too low. It senses low system pressure, high compressor temperature, current flow melts a fusible link in the thermal limiter and stops current to the compressor clutch. If this does happen, you are actually replacing a fusible link and finding the original problem on why that fusible link burned in two. Pressure relief valve bleeds off excess pressure to prevent compressor damage. We don't see too much of this anymore because we don't want to bleed off refrigerant into the atmosphere. But in years past, we did have a pop-off style valve on the receiver dryer or the compressor or some component on the high side of the system to bleed off excess pressure. We don't see this too much anymore. Wide open throttle. And if you think about this just a little bit, you understand that the compressor takes energy to rotate. Well, that's taking away horsepower. So what the industry has done is they've installed a wide open throttle switch that when you put your accelerator pedal to the floor, the computer and the engineer assumes that you want as much power to the wheels that you possibly can put there. So what they're going to do is they're going to shut off the air conditioner compressor at wide open throttle to give you as much power as you need to get done what they assume that you want to do when you push the throttle to the floor of the interior compartment. An AC switch, really this is just a driver operated switch in the car's dash that feeds current to the compressor clutch. This might have a snowflake icon on it. This might say AC. This may just be a little blue light that comes on when you push it. But a lot of companies have put a separate switch on the dashboard that you have to push to engage the compressor. That's the AC switch. There's been a lot of air conditioners that I have repaired by just simply instructing the customer how to push the little snowflake button on the dashboard. It sounds rather funny, but when you're talking to a customer that may have just purchased this car, they may have gone from a GM product to a Toyota product, and their GM product didn't have an AC switch, but the Toyota does. And so they're not familiar with the fact that they have to push the little snowflake button to get the air conditioning system to work. So be aware of that. Normally at this time, I would ask if there's any questions on the refrigerant side of the air conditioning system. That pretty much concludes the refrigerant side of the air conditioning system. And we're going to be getting into the heating system. This usually goes pretty quick because at this point, a lot of you have already experienced pretty much everything that's in the heating side of the air conditioning system. And as you can see in the diagram that's on the screen in front of you right now, what consists in that heating system. You've got a radiator, you've got your upper and lower radiator hoses, you have a thermostat that's going to control the flow of the coolant from the engine to the radiator, and then you've got your two smaller heater hoses that are going to your heater core. Now the heater core is located inside that box that we looked at before. It's located in the same box that the air conditioning evaporator is located in, and the blend doors are going to be what's going to control the airflow either over the air conditioner evaporator or over the heater core or over both. We can run air over both, either to humidify the air during the wintertime. We might be running air over the evaporator to mix with the heater core air to actually humidify the air during wintertime, or we might be running air over the heater core during the summertime to dehumidify that. So these systems work together in that plastic box underneath the dashboard or behind the glove box. So this is using the engine's cooling system to heat the passenger compartment in cold weather. Remember, the cooling system's job is to remove heat from the engine. So actually what we're doing here is we're just using that heat that we removed from the engine to warm the passenger compartment. Usually consists of two heater hoses, a heater core, and then we've got a blower motor that's going to blow over that heater core. Okay, in the temperature control systems, these can be automatic or manual. And the old manual systems, these used either a lever that went back and forth. You chose the mode you wanted, whether it was the floor, through the vents in the dash, or through the defroster vents, or a combination of any of those. That's the mode. And sometimes in the past we had a slide. Some of the newer ones we have an actual dial that you're going to select the mode. And then we have a temperature slide or a temperature dial that you're going to select the temperature of that. And then you would have a third lever or dial that you're going to control the fan speed. And these are the old manual systems, and I'm sure some of you have those. But now we're starting to get into either semi-automatic or full automatic systems. An electric switch may operate usually through relays. There's a blower motor, there's a compressor clutch and other electronic components, some of which you've already covered in the electronics class. That blower motor, depending on how many speeds you have, the older cars had only 3 speeds. I've seen as high as 6 fan speeds in some newer cars. And remember, all you're doing on those speeds is you are going from 0 volts, that would be off, to full 12 volts for the highest fan speed. So all of the other speeds in between are just your voltage is being going through a resistor. So it's actually less than 12 volts depending on the size of the resistance. So fan speed number 1, or the slowest speed, might have lots of resistance, and the speed next to high will have just very little resistance. And of course your high speed is going to be no resistance at all. So there's a blower motor resistor somewhere in all these systems. You can either have mechanical levers and cables that operate the doors. We haven't seen those since probably the mid to late 1970s. Vacuum switches or vacuum diaphragms have been used for many, many years. We were still using those much through even the early 2000s, where you had a vacuum diaphragm that would open and close the either the blend doors for the temperature or the mode doors to direct the air on the defrost vents, the center vents, or the floor vents. Now we do have in recent years electronic control units and sensors that operate the heating and air conditioning systems automatically. Anywhere from an electric door that's going to be moving the electric motor operating the doors, the mode doors, the blend doors, and now we're getting in systems that are split. That's very common now that we have systems that are split right to left, where the driver has their controls and the passenger has their controls, and even getting into systems that are for the middle passengers in an SUV and the passengers in the rear. I have seen what we call 4-zone systems. And what that means is you have 4 zones that are being controlled by this automatic temperature control system. So you'll have a driver's zone, you'll have a passenger side zone, and you'll have a mid-passenger zone for the middle passengers in an SUV. And then you'll have a rear zone for the rear passengers in an SUV. And each zone can be controlled separately. And they are controlling these through these blend doors and these mode doors. Most of these are fully automatic systems. So you can imagine the sensors involved. So here's some pictures of some different control heads. The manual temperature control heads on the left, whether that be slides or dials. You can see on the upper one, on the left, you have a separate AC button. That's what I mentioned earlier. And so if you wanted the compressor to kick in, you would have to press that button that actually said AC. And that's what's going to engage the air conditioner compressor. And some people don't know what that even exists, or that they have to push that to get the compressor to engage. So no refrigerant flow, no cold air. And then you've got your fan speed on the dial on the left. You got your temperature control in the middle, or the blend, or temperature blend in the middle. And then you have your mode selection on the far right in that first picture on the top left. The one on the bottom there, on the bottom left, is an older style that's semi-automatic. You can still pick the mode, but the temperature part, or the temperature blend, is going to be automatic. But you still had to physically select the mode and the fan speed. So that's a semi-automatic system. Picture on the right, that is a fully automatic system. So, and obviously that's taken out of the vehicle right now, but in that black screen you would see the temperature that you are setting it at, and then based on the sensors placed throughout the interior of the vehicle, the car is actually going to automatically control the mode, the fan speed, and the blend of the temperatures over the heater core or the air conditioner evaporator to achieve the temperature that you set it at. So this works a lot like your central air unit in your house or in a business. Obviously, this is going to require many more sensors throughout the interior compartment so that the computer knows what the input is, what the temperature is, what the humidity is, what the ambient temperature is, what the radiation, heat radiation is through the windows. And so there's a lot of sensors involved with that. Now, I want to, in this next photo here, this is something that's very common that we see in vehicles coming into your shop, all of the debris at the base of the windshield. I want to point out, students, that that is where the outside air is coming in from. So if you have an air conditioning or the system set to heat, the air conditioning system is pulling air from the outside, and that grill work at the base of the windshield is where that air is coming from. So unless you press the recirculate button on the control head, the default is pulling air from the outside. If this grill work is all covered up with leaves and debris, and for a person that parks outside on a regular basis, this is a very normal condition, then these vents can be blocked. That's a possibility. Or that debris, as it gets crushed and put into smaller pieces, is going to fall through those cracks and actually go into the heater box or the box inside the dashboard. And then we've got other problems and blockages. This could create blockages in airways, and this also could create blockages in the passenger compartment filters. This is something fairly new within the last decade, that we now have these passenger compartment filters that can become clogged. These are a high efficiency filter. This helps prevent allergies by trapping pollen and other particles in air. However, what this can also do is, if this is never changed, the passenger compartment filter is never changed, then this could create a blockage, an air blockage. And we quite often see customers coming in and they're complaining about that either the air is cold like it's supposed to be, but it's not blowing with the forcefulness that they expect out of the vents. Or same with the heater. The heater is hot, but it's not blowing with the forcefulness it should. They can hear the fan, but they don't really feel it. And that's an air blockage in that box. And it's very possible that all that debris that's built up is now down in that filter. And we have passenger compartment filters that get plugged up. I've even pulled some out of vehicles that actually have small little plants growing in the filter. And that's from tree seeds or plant seeds coming through that grill work. Add in dirt, add in moisture from the air, and you've got a perfect climate to start growing plants. And I have pulled these out that have little sprouts that have come out of that filter. That is well overdue. But if you have a vehicle that have these passenger car compartment filters, it's important to change them on a regular basis, or at least check them on a regular basis. And that might involve pulling the glove box door down and pulling it out, or in some cases this is pulled out on the engine compartment side, and they'll have a little trap door that you fold down and change it out from there. Well, that is pretty much going to conclude the air conditioning basics. I want to encourage you that if you do have any questions, please, you need to call, text me. There are many ways you can get a hold of me. If you do have questions about this, I really expect some feedback from you. If you're having problems understanding something, just give me a call, give me a text message or a Facebook message. I don't care how you do it. Just do something so that I can get you straightened out. Okay? We will talk at another time.